module of the Juniper Network's Design Fundamentals course. So for the objectives, we're going to look at the best practices and considerations when designing a data center. Alright, so data centers obviously vary in size, shape, and sophistication. So one size fits all, that design doesn't work. So what we see here on the screen, we have some questions that can help you figure this out. First, does your data center generate revenue or support internal IT and campus environments? This relates to the customer's data center segmentation. Second, besides your primary data center, how many additional ones do you have? Do they need to be connected? This offers insight into extra data center opportunities. Third, what's the growth plan for server farms over the next 2 years? Is there a plan for 40 gigabit Ethernet, 100 gigabit Ethernet, or even 400 gigabit Ethernet? This shows the expansion and growth in the data center, hinting at which types of switches you need. Fourth, what kind of performance is required? This offers information about latency needs, wire speed, deployment, also pointing to the necessary switches. Fifth, does the customer require traffic separation or SLAs? This informs whether they must meet service provider specifications. So data centers have varying sizes, performance needs, and price constraints. Also, motivations behind adopting new technologies differ. A finance firm might explore new tech to get an edge on the competition, while traditional IT companies could be a bit more conservative about that. So there's no one-size-fits-all solution. The chosen technology depends on the business's nature. So categorizing by the number of servers, it can be misleading, as different data centers might need the same server count, but require different switch infrastructures. So 3 general data center categories exist with differing requirements. Enterprise IT data centers, focusing on capital and operating expenditures, aim for cost control and might converge storage on LAN networks for efficiency. Cloud providers form the second category, needing massive scale due to millions of users. Hence, cost is going to be a major factor for them. Performance-oriented data centers like financial or research companies prioritize network speed. In finance, revenue depends on quick transaction completion, so low latency and low jitter are absolutely critical. High-performance computing firms also fall into this category. Data centers can be classified as IT or production data centers. IT data centers, being cost centers, focus on cost control. They are interested in server virtualization and convergence. Conversely, production data centers, being profit centers, prioritize revenue generation. Their focus is performance, scale, and cost-effective operation. They're dynamic and require agile infrastructure for different connections. While convergence might be of interest, their main focus is server number increase and dynamic application provisioning. All right, so as a seasoned IT professional, you're undoubtedly aware of how critical a well-designed data center is to the efficiency and success of an organization. So let's unpack the points that we see here on the screen together. So firstly, one of our core objectives is to lower the total cost of operation while ensuring investment protection. This isn't just about saving money. It's about optimizing resources, ensuring sustainability, and laying the groundwork for future expansion and adaptability. Speaking of optimization, physical layer efficiency stands out. This means making the most of our energy and space. We're talking about green computing, utilizing resources in a manner that's environmentally responsible and economically viable. Given the global push towards sustainability, achieving efficiency in these areas is both an ethical and also a strategic choice. Next, let's discuss data center consolidation. As our technology landscape grows, there's a compelling case to centralize our resources. By doing so, we can reduce redundancies, streamline processes, and bolster our disaster recovery measures. Okay, so ensuring our data center environment is simple, high-performing, and highly available is non-negotiable. Users demand increased bandwidth and lower latency. These are not just metrics. They define the user experience and productivity. Furthermore, high availability combined with reliability and modular scalability ensures our services remain uninterrupted and adaptable to changing demands. The architecture also matters. A simple, flatter network can improve data flow, reduce bottlenecks, and also simplify troubleshooting. With the rise of diverse storage solutions and integrated systems, storage awareness, network convergence, and virtualization become absolutely paramount. Lastly, we must always be aware of users and applications. It's so easy to get caught up in the hardware and metrics, but our systems serve people and processes at the end of the day. Ensuring a seamless integration of user application, network, and security policies provide a cohesive environment. And by enabling layer 2 mobility throughout the data center, we ensure flexibility and adaptability for our services and applications. All right, so traffic patterns in data centers. What do you think? Do they matter? They definitely matter. So understanding traffic patterns is key to determining the optimal data center design. So this layout that we see here is based on a class architecture. Highlights traffic directions east-west or north-south, and they shape the capacity of uplinks between layers, including the WAN link. So as we talked about earlier, the access tier is the network's entry point for compute and storage resources, forming the data center's backbone. Its size and structure influence the other tiers and the entire network size. So while a larger switch with more access ports at the access layer might reduce this east-west traffic flows, this isn't an economically scalable solution. Also, it's incompatible with the current and foreseeable placement of access switches due to rack space and environmental factors. You have to do something different to suit the standard switch placement and mitigate northbound traffic. So the initial step is to expand the access tier and streamline and scale it to the data center network. This leads to fewer access switches, allowing direct rack-to-rack traffic bypassing the aggregation or core layer. This results in fewer uplinks to the aggregation tier, possibly eliminating it altogether. But how do we reduce access tier switches and enable cross-rack server traffic? One option is to use virtual chassis. This allows up to 10 switches to interconnect via high-speed connections, functioning together as a single chassis. Servers connected to different members of the virtual chassis can communicate through the virtual backplane, avoiding these upper tiers. You could deploy 2 virtual chassis spanning the same racks for enhanced availability. Servers can be dual home to each virtual chassis. Depending on the environmental requirements, you may only need 2 uplinks from these 10 top-of-rack switches, now part of a single virtual chassis, which reduces the number of uplinks to the aggregation tier. So benefits of virtual chassis include simplified management, network design, increased resilience, flexibility, and superior performance, all at a lower cost. All switches can be managed as one logical entity. The physical placement of member switches is so very flexible, spanning racks, floors, buildings, or even different facilities. All right, so this screen shows some performance benefits of virtual chassis. When deployed at the access tier, traffic between servers and racks via the virtual chassis doesn't need to pass through the upper tier. This streamlined design leads to a more efficient traffic path. The screen also shows a common scenario benefiting from this performance boost: migration of VMs between servers in different racks. They're connected to the same logical switch, and so there is no need to track the migration of the VM from one switch or rack to another. All right, so let's talk about security. So integrating security into the data center design is absolutely critical. And I hope by this point, you've gotten the idea that every part of the network absolutely needs security. As data centers expand and complexity increases, potential points of vulnerability also increases. A secure yet user-friendly environment is absolutely vital for operations. In data center security, you should adopt what we call a zero-trust model. This approach assumes all network requests are untrusted until validated. It involves robust identity verification, multi-factor authentication, constant monitoring, and stringent access controls to safeguard the data and systems. No domain within the data center is completely trusted, as any could be origins of attacks. Network administrators set acceptance policies to control inbound traffic, ensuring policy compliance. North to south and east to west traffic are both evaluated for security. High-end SRX series devices process all visible traffic at the perimeter. However, only layer 3 inter-subnet traffic within the data center is typically processed by physical SRX series devices. Layer 2 traffic within the data center generally is trusted and not evaluated. However, for this traffic, we can do selective traffic evaluation using filter-based forwarding in the data center. Okay, so visibility is difficult for inter-VM traffic within the same virtualized server. This is also considered east-to-west traffic. A VSRX instance can be deployed in the virtualized server for traffic visibility, evaluation, and policy enforcement. So after firing up a VSRX, configure the server's virtual switches to ensure all inter-VM traffic within a server passes through the VSRX VM. Okay, so planning the physical layout of the data center is an essential step to its design. It's not just about selling and deploying devices. The data center is often divided into segments or zones, each comprising multiple racks of computing, storage, and network equipment. So physical factors in the data center design include equipment placement, cabling needs, power, and cooling. So once a good layout is determined, it can be replicated across all segments or even in different data centers. A modular design like this helps with scalability, reduces complexity, and simplifies operations. All good things for the data center or any networks really. So balancing the efficiency of equipment deployment with cable length restrictions and other physical factors is absolutely key for networking device layout in the data center. You'll have to weigh the benefits and drawbacks of consolidating network devices in a single rack versus distributing them across multiple racks. Efficient solutions at the rack and row levels ensure overall design efficiency, since these elements are replicated across the data center. All right, so that brings us to the end of this module. In this module, we talked about the best practices and considerations when designing a data center.